Hello friends, welcome in a lecture of Dynamics of Machinery subject. Myself Mitesh Patel. I am a assistant professor in a mechanical department at a Dr. Subhas Technical Campus, Junagadh. Today's our lecture topic is a critical speed of shaft when the shaft is carrying the multiple rotor. Okay. So in this lecture we discuss or solve the examples of this topic of a critical speed of shaft for a multi-rotor. Okay, so first we solve the example of a critical speed of shaft for a multiple rotor. We recall the what is the critical speed of shaft. It's a one speed, one particular speed for a rotation of shaft. At the speed, shaft of vibration is too much high. And why this happen? Due to the resonance. At that particular speed of shaft, rotational speed of shaft, the frequency of unbalanced force or forces are matched with the frequency of vibration of shaft, and at that case the resonance is created and the amplitude of vibration is too much high. So at that speed of the shaft, when the resonance is created, is called the critical speed for shaft or critical speed of shaft. Okay, so now here the critical speed of shaft we have to find out, or we find out the amplitude of shaft when it's rotate, when the rotor are multiple which are mounted onto the shaft, when the shaft carrying the multiple rotor. Okay, so let's start the solve to example. First example data is given. Shaft of 50 mm diameter and 3 meter length. The shaft dimension is given. Diameter of shaft is a 50 mm and the length of shaft is a 3 meter. Okay, and the other data is given. Mass of 10 kg per meter length. Mass of 10 kg per meter length. It is simply supported at the end and carries three masses of 70, 90 and 50 kg. The mass is given 10 kg per meter length, means the self weight of shaft, it's a 10 kg per meter length of shaft, means the shaft 1 meter length of shaft having a 10 kg weight. Okay, it's a self weight of shaft and it's simply supported at the end and carries the three masses 70, 90 and 50 kg at a 1 meter, 2 meter and 2.5 meter distance from the left support. So in this figure is defined the three mass are placed at a 1 meter from the left support, 2 meter from the left support and 2.5 meter from the left support. Mass 1, mass 2 and mass 3 are placed onto the shaft. Okay, mass 1 70 kg, mass 2 90 kg and mass 3 50 kg. Okay, now find the natural frequency of transverse vibration. Okay, we have to find out the natural frequency of transverse vibration, and the modulus of elasticity is given for a material of shaft. Okay, for a shaft is given. Okay, now for the multiple rotor carrying the shaft, in that case the vibration or natural frequency is find out with the help of two methods. One is the Dunkerley method and second one is the Rayleigh's method. And generally the almost example are solved with the Dunkerley method, and it's very easy to solve the example by Dunkerley method. It's very simple, so we use the Dunkerley method to solve the example of multiple rotor carrying the shaft. Okay, so this example solved with the Dunkerley method. Okay, and we know that In Dunkerley method, this equation is given the particular circular frequency for a critical speed and frequency of critical speed of shaft. Okay. So first of all, we have to find out the omega C1, omega C2, omega C3, omega C4 and omega Cs. So what is the first omega C1? Omega C1 is the circular frequency for a mass 1, circular frequency for a mass 2, circular frequency for a mass 3 or circular frequency for a mass 4, omega C4. But the individual mass frequency, not any other mass is considered. Let's understand with the figure. If you consider for the mass 1, then mass 2 and mass 3 are not considered. Only mass 1 is considered, and also sulfide of shaft is not considered. Only mass 1 is considered, or a single rotor is considered, and for that case the omega C1 is find out for the single rotor. Then this rotor is removed, this rotor is removed, only rotor 2 is placed onto the shaft, and then for this rotor we have to find out the omega C2, the circular frequency of our rotor 2. And similarly for the rotor 3 is considered, the rotor 1 and rotor 2 is not considered, only rotor 3 is considered, means the shaft having only one rotor, rotor number 3. Okay, and for that case we have to find out the omega C3. Okay, and after find out these, we have to find out the omega Cs. This is the circular frequency of shaft due to the sulfide, by considering the sulfide, not considering the any rotor, only consider the sulfide of shaft, and at that case only shaft is rotated without carrying the any rotors or mass, and for that case we have to find out the circular frequency, and this circular frequency is denominated by omega Cs. Okay, so through Dunkerley method we have to solve this example or find out the frequency. We have to find out the omega C, and omega C equation for a Dunkerley method is a 1 upon omega C square is equal to 1 upon omega C1 square plus 1 upon omega C2 square plus 1 upon omega C3 square plus 1 upon omega C4 square plus 1 upon omega Cs square. Okay, so first we have to find out the all value of omega C1, omega C2, omega C3, omega C4 and omega Cs. Okay, now we have to find out the all omegas value, and how we have to find out? With the help of this equation, under root G upon delta. So for omega C1, the equation is a G upon delta 1. Delta 1 is the static deflection generated due to the only rotor 1, not considering the rotor 2 and rotor 3. Only place the rotor 1 on shaft at a specific distance which are given into the data, and the deflection is measured. This is the delta 1. Similarly, delta 2 is a deflection due to the rotor 2, and not considering the rotor 1 and rotor 3. Only place the rotor 2 on shaft, and due to this rotor the deflection is occur onto the shaft is considered delta 2, and delta 3 is deflection due to the rotor 3. Okay, only rotor 3, not considering the rotor 1 and rotor 2. Okay, so how the delta is find out? The delta is find out, value of delta is find out with the help of simply supported beam deflection equation. The shaft is considered as a simply supported beam, the bearing is supported to the shaft, and bearing is considered as a simply support, and the shaft is considered as a beam, and the shaft carrying the sulfide is considered as a distributed load, and the rotor of weight or mass given is a point load, considered as a point load. Okay. So this figure is indicate the all things in form of beam. Okay, for given condition or data of example. Now the static deflection equation for simply supported beam for a point load when in center or when in out of center is different. Okay, when point load is not center in a simply supported beam, then the deflection of beam for a simply supported is a m2g means w L1 square L2 square upon 3EIL. Okay, L1 is the distance of point load from the left side and L2 is the distance of shaft from the right side of the support. Okay, ready? And L is the total length of shaft or beam. Okay, and E is the modulus of elasticity and W is the weight, and here delta 2 is considered, so the weight is considered for only rotor 2. Okay, so here put the value of M2 is a 90 kg for a rotor 2, G is a 9.81, L1 for a rotor 2 is a 2 meter, and L2 square, so L2 value for a rotor 2, L2 is a 1. Okay, and total length of shaft is a 3 meter, so here 3. Mass moment of inertia for a shaft, circular section shaft is a pi by 64 d raised to 4. D is given or A is given in mm, so convert into the meter. Okay, and capital is the Young modulus, the value is given of Young modulus. Okay, so we find out the value of delta 2. Similarly, we have to find out the value of delta 1 and delta 3. For a delta 1, only consider the mass or point load 1 or rotor 1. For a W, the weight is considered for only rotor 1, 70 kg, and multiply by G, 9.81. L1 is a left side distance from the support from rotor is a 1 meter for a rotor 1 or point load 1. Okay, it's a 1 meter, and L2 is a distance from the support to point load from right side, from right support. Okay, is a 2 meter for point load 1 or rotor 1. Okay, and the total length is a 3 meter, and mass moment of inertia is similar for the all delta pi by 64 d4 d raised to 4, and E value is also same for the all rotor. The shaft and rotor are made with the same material, and mass is given 70 kg. Okay, and finally we get the value of delta 1. Similarly, we get the value of delta 3 from the same equation. Here L1 for a rotor 3 is a 2.5 meter, and L2 is the 0.5 meter for a rotor 3, and total length we know that 3 meter, and mass moment of inertia and capital value is all same for the all delta, and mass of rotor 3 is a 50 kg. Okay, and we get the value of delta 3. Now we have to find out the value of omega cs. We have to find out the static deflection generated due to the self weight of shaft. If the length of shaft is high, then if you observe that when it support with the two simply support at the end, then shaft is bent due to the self weight. So we consider the deflection, static deflection due to the safe weight of shaft. Means the no any rotor on shaft, and only shaft is mounted onto the bearing, but due to the own weight of shaft, the shaft is deflected, or deflection, static deflection, delta S, and the delta S is the static deflection is defined by UDL, uniformly distributed load on the shaft. And for a simply supported beam is loaded with the UDL, and for that the deflection of beam is find out with the equation. The equation of distributed load for a simply supported beam for that case is change compared to point load. It's a 5 mg L4 L raised to 4 384 EI. Capital E and I, mass moment of inertia and Young modulus, is same as it is for delta 1, delta 2 and delta 3, and L value is 3 meter, we know that, and the mass is considered for the shaft is 10 kg per meter. So here the 10 kg, because the load is considered as a UDL, uniformly distributed load, per meter. So per meter mass is given 10 kg, and we put the value and multiply by 9.81. So W value is apply on this equation. Now finally we get the value of delta S, and from that delta we can find out the value of omega C1, omega C2, omega C3 and omega CS. Okay, so we finally get the value of all omega and put the value of all omega in the Dunkerley equation, Dunkerley method equation, and finally we get the value of critical speed of shaft, and from that we can find out the frequency of shaft, omega c upon 2 pi. Okay, so we get the value of omega c 26.4 radian per second, and fc is the frequency f is equal to 4.202 hertz. Okay, now see the other example. A 50 mm diameter shaft of 3 meter long has a mass of 20 kg per meter length. Okay, it is simply supported at its end and has a 3 mass 100, 150 and 50 kg at a distance 0.9 meter, 0.16 meter and 0.24 meter apart from left end support. Final, the frequency of transverse vibration by Dunkerley method, and capital E is equal to 205 gigapascal. Modulus of elasticity value is given. Okay, so the dimension of shaft is given 50 mm diameter, it's converted into the meter. Okay, 0.05 meter, and length of shaft is given 3 meter. The weight of shaft per meter is a mg. It's a 198.2 Newton per meter. Okay, weight of shaft is a 198.2 Newton per meter. Okay, it is simply supported. Okay, the shaft is simply supported, consider, with the help of bearing, two bearing at the end of shaft as shown in figure. Now this three mass 1, 2 and 3 distance are given from the left side is the 0.9, 0.16 and 0.24, and this is the case for multiple rotor carrying the shaft, and for that case we know that the Dunkerley method is useful and easy to find out the frequency of vibration for a shaft, okay, when carrying the multiple rotor. So here already mentioned the Dunkerley method, so we know that how to find out the frequency with the help of Dunkerley method. First we have to find out the angular speed of shaft omega with help of Dunkerley method equation. So we have to find out the omega 1, omega 2, omega 3 and omega 4 for static deflection of shaft. Omega 4, okay. So first of all we have to find out the delta 1, delta 2, delta 3 and delta 4. So we know that the shaft is considered as a simply supported and the point load is considered of a given mass is considered as a point load for a beam, and for that when the point load are applied onto the beam on which are supported simply, then the deflection of beam is found out with the help of this equation W L1 square L2 square upon 3 EI L, okay. So now for a delta 1 we know that only consider the mass M1, not considering the any other mass. Self mass or self weight of shaft is also not considered, second mass is not considered and third mass is also not considered. Only consider the single mass M1, okay. So this figure is defined individually single mass rather than all three mass, okay. So for the case of delta 1, here the L1 value is 0.9 meter from the left side of support, and from the right side is a 2.1 L2. L is a total length is a 3 meter, and E value Young modulus value is given, and the value of I is a pi by 64 d raised to 4 for a circular section shaft, okay, and it's already find out. The value of D is given 0.05 meter, so we find out the first mass moment of inertia about the axis and put the value of all things. And here W1 is the weight of mass 1, so M into G. The mass is given here for a single mass is given is a 100 kg for M1 mass is a 100 kg and multiplied by 9.81 is a 981 Newton for single mass, single weight, okay. The weight is a 981, and finally we get the value of delta 1 6.2 into 10 raised to minus 3 meter. Similarly we find out the value of delta 2 by considering the only mass 2 or weight 2, not considering the mass or weight of rotor 1 and rotor 3, and not also consider the self weight of shaft, only consider the weight of second rotor, and the equation is given for a delta, and L1 L2 and L value is put, E and I is a same for the all delta, and the weight of rotor is given, okay. So we find out the value of delta 2, and it's already we can easily find out with this equation. Similarly the value of delta 3 we have to find out, and we know that how to find out with the help of this equation. And L1, L2 and L value is there. L1 value is the 0.24 from the left side for a rotor 3, and the right side distance from the right side support is a 0.06. Okay, so L2 value is a 0.06 and total length value is a 3 meter. L1 value is 0.24, L2 value is a 0.06 for a rotor 3. Here only rotor 3 is considered, rotor 1, rotor 2 and self height of shaft is not considered. Okay, so finally we get the value of delta 3, and finally we have to find out the value of delta 4, and for that we have considered the distributed load UDL for a self height of shaft, and it's given a 20 kg per meter, and it's converted into the Newton, 198.2 Newton per meter. Okay, so for a UDL apply onto the simply supported beam, and for that condition the deflection equation is a 5 into WL square L raised to 4 upon 384 EI. Put the value of all element, and finally we get the value of delta 4. It's a static deflection due to the own weight of shaft or a self weight of shaft. Okay, now put the value of all datas and find the value of omega 1, omega 2, omega 3 and omega 4, and this all omega's value apply onto the Dunkerley equation, and finally we get the value of omega for a shaft when carrying the multiple rotors simultaneously. Okay, and from that we can find out the frequency omega upon 2 pi. Okay, and the frequency is a 3.19 hertz. Now see the another example of beam, and that types of example is also asked into exam. If example is not given in form of shaft, so you have to remember that the Dunkerley method is applied for to the shaft, and shaft is considered as a simply supported beam. The example to solve for that case you given in form of the beam. So here example of beam is given for a Dunkerley method. Okay, so we solve the example of beam, and we know that if the shaft is given, then shaft is given as a beam. Here directly beam is given, so nothing change in to solve the methods to solve the example. It's the same method but directly given the beam. If the shaft is given, then we consider the first shaft and then convert into the figure of beam or consider as a beam. Okay, here directly beam is given, so we have to find out the frequency of beam with the help of Dunkerley method. Here two mass are given. Okay, so here one thing is changed, the beam is not simply supported but is the cantilever beam. Okay, so for that the deflection equation is changed, and here the deflection is defined by y. Okay, and you can also define by delta. The deflection equation for a cantilever beam for a point load is WL cube by 3 EI. Okay, so L is the total length of shaft, I is the mass moment of inertia for shaft or beam, or beam mass moment of inertia is given in figure, and this figure is also given in the question or data. So directly given the value of E and I. So put the value in this equation, and for a mass 1, this equation, or for delta 1, if we consider the equation for a delta 1, then W is a 100 into G for a delta 1. Okay, and the total length is a, sorry, here the not total length is considered, here the length is considered from the support to mass. So here the mass is a 100 kg is considered, so the distance from the support is a 180. So 180 is considered, 180 mm is considered, and it's converted into the meter, it's multiplied by 10 raised to minus 3. And now we get the value of deflection delta 1 or y1. Okay, now we find out the deflection y2 or delta 2 for a mass 2 or weight 2. Okay, so only consider the weight 2, 50 kg, not considering the 100 kg, and here the value of mass is a 50 into 9.81. The length is a 180 plus 120 is a 300 mm. It's converted into the meter, 10 raised to minus 3 multiply, and E and I value is given, Young modulus and mass moment of inertia value is given in data. So directly we put the value and directly get the value of delta 2 is a 5.631 into 10 raised to minus 5 meter. Okay, we have a now delta value, so we find out the omega value, omega 1 and omega 2, with the help of G upon delta equation. Here delta is defined by y, so G upon y. Y1 and y2 we already find out, so put the directly value of y1 and y2 in omega n1 and omega n2 equation, and we get the value of omega 1 and omega 2, 635.116 radian per second and for 117.40 radian per second. Now the omega value is applied onto the Dunkerle equation, and finally we get the value of circular frequency omega n, 348.81 radian per second, and from that we can find out the frequency value omega n upon 2 pi, and so Fn is find out with the help of dividing by 2 pi, and Fn value is the frequency of beam is a 55.51 hertz. Okay, so I hope that you very well understand the critical speed of shaft for a multi-rotor when shaft is carrying a multi-rotor, and the examples of critical speed of shaft when shaft carrying the multiple rotor. Okay, thank you for listening my lecture, and if you have any query then ask to me. Thank you again.